Imagine a world where your application needs to scale effortlessly, handling millions of users, thousands of transactions per second, and unpredictable traffic spikes. You want performance without having to worry about provisioning servers, maintaining infrastructure, or dealing with complex scaling logic. This is the world AWS DynamoDB was built for. DynamoDB is a fully managed NoSQL database service provided by Amazon Web Services. Unlike traditional relational databases, DynamoDB is designed to handle massive workloads with low latency performance, even under heavy traffic. At its core, it offers key value and document data models, which means you can store, retrieve, and query data in a highly flexible way. What makes DynamoDB stand out is its serverless nature. There's no need to manage hardware or clusters. Amazon handles everything behind the scenes, from data replication to fault tolerance, ensuring your application stays fast and available across multiple regions if needed. Each item in a DynamoDB table is uniquely identified by a primary key. This primary key can either be a simple partition key or a composite of partition and sort keys. The partition key determines how the data is distributed across partitions, which is a key factor in achieving efficient performance. When you add a sort key, you're introducing the ability to store multiple items with the same partition key and query them in a sorted order. DynamoDB also offers powerful query capabilities. You can retrieve data using primary keys, filter results using expressions, and even scan through an entire table if needed. Although scanning is less efficient than querying, it's useful when you want to process or analyze large datasets. For applications that demand lightning-fast performance, DynamoDB Accelerator, known as DAX, offers in-memory caching to reduce response times from milliseconds to microseconds. And if your workload involves time-based or infrequently accessed data, features like TTL, or time to live, allow you to automatically remove old data, keeping your tables clean and cost-effective. Security is another strength of DynamoDB. It integrates seamlessly with AWS Identity and Access Management, allowing you to control who can read from or write to your tables. You can also enable encryption at rest and in transit, ensuring your data stays secure at all times. In the background, DynamoDB automatically replicates your data across multiple availability zones within a region, providing high availability and durability. For mission-critical applications, you can even enable global tables to replicate your data across multiple AWS regions, offering multi-region, multi-master replication. All of this power is accessible through the AWS SDKs, CLI, and the Web Console. Developers can easily integrate DynamoDB into their applications using familiar tools and languages, from Python and JavaScript to Java and Go. Whether you're building a real-time gaming leaderboard, managing session data for millions of users, or creating a scalable e-commerce backend, DynamoDB is engineered to handle it all with grace and speed. Let's move on to the next chapter in your DynamoDB audiobook. Here's a continuation, focusing on table design strategies, with the same natural, engaging tone. To truly unlock the power of DynamoDB, understanding how to design your tables properly is essential. Unlike traditional relational databases where normalization is the norm, DynamoDB thrives on a different approach, one that embraces denormalization and anticipates access patterns right from the start. In DynamoDB, everything begins with your application's access patterns. Instead of thinking in terms of tables and joins, you begin by asking, what kind of queries will my app need to support? What kind of data will users want to fetch? And how fast do I need those responses to be? From there, you design your table and its keys. Every table must have a primary key, and this is where your strategy begins. If your application only ever needs to fetch one item at a time, say, a user profile or a single product, then a simple primary key made up of a single partition key is enough. But if your app needs to retrieve groups of related data, like all orders made by a customer or all messages in a chat room, you'll want a composite primary key. That's where the combination of a partition key and a sort key comes into play. DynamoDB doesn't support joins like traditional SQL databases. Instead, it encourages you to put all the related data in the same item or group of items. This often means storing redundant data or nested objects within a single item. While this might seem counterintuitive at first, it's actually what makes DynamoDB so fast. It reduces the need for multiple reads and allows you to fetch everything you need in a single query. Indexes are another important part of table design. When your primary key alone isn't enough to support all your access patterns, you can turn to secondary indexes. There are two kinds: global secondary indexes and local secondary indexes. A global secondary index, or GSI, lets you query your table using a different partition key and sort key than your primary one. It's incredibly useful when your app needs to look up data in more than one way. A local secondary index, or LSI, Lets you define additional sort keys for the same partition key. Great for filtering and ordering data within a single group. But with power comes responsibility. Secondary indexes come with their own storage and performance considerations. They consume read and write capacity, and they replicate a portion of your data, so it's important to use them strategically. Another best practice in table design is to model your data around single table design. Instead of creating one table per entity, like users, products, or orders, you store multiple types of items in the same table. Each item is distinguished by a combination of key values and attribute names. This might sound complex, but it allows you to perform queries across item types and access everything you need with fewer reads. It's a shift in mindset. Rather than designing your schema first and hoping the access patterns will fit, you do the opposite. Start with how you need to read the data, then shape your schema around those needs. Planning your access patterns ahead of time helps prevent costly redesigns later. And thanks to DynamoDB's flexibility, you can evolve your schema over time, adding new attributes or types without needing to restructure existing data. So when designing your DynamoDB tables, remember, performance comes from simplicity, and simplicity comes from planning. Think like your application. See the world through the eyes of your queries, and shape your tables to deliver exactly what you need, fast and efficiently. Let's dive into DynamoDB pricing and capacity models next, continuing in the same smooth, audiobook-ready style. When working with any cloud service, understanding pricing is just as important as understanding how it works. With DynamoDB, Amazon offers a pricing model that's built for flexibility, giving you the choice between on-demand and provision capacity. The right choice depends entirely on your application's traffic patterns and predictability. Let's start with on-demand capacity mode. This is the simplest option. You don't need to specify how many reads or writes your application might perform. DynamoDB automatically scales up and down as needed, and you're billed per request. This mode is perfect for applications with unpredictable or spiky workloads, maybe a startup app going viral, or a seasonal platform that sees huge traffic one week and almost none the next. With on-demand, you're paying only for what you use, and you get the benefit of automatic performance scaling without needing to manage anything. But if your workload is more predictable, or if you're operating at scale and want to optimize costs, you might consider provisioned capacity mode. Here, you tell DynamoDB how much read and write throughput you need. This is measured in read capacity units, RCUs, and write capacity units, WCUs. One RCU supports one strongly consistent read per second, or two eventually consistent reads, for items up to 4 kilobytes in size. One WCU supports one write per second, for items up to 1 kilobyte. Provisioned capacity gives you more control, and when you pair it with autoscaling, DynamoDB can adjust your capacity up and down within limits that you define, helping you save money without sacrificing performance. For workloads that are read-heavy and require even faster performance, you can also add DynamoDB Accelerator, or DAX. DAX is an in-memory caching layer that sits in front of DynamoDB and can deliver microsecond response times. It's priced separately, based on the number and size of DAX nodes you use, and it's especially valuable for applications like gaming, ad tech, or real-time analytics. Another cost-related feature worth knowing is reserved capacity. If you're running at high throughput and have consistent usage, you can commit to a 1-year or 3-year term to receive significant discounts. It's like buying in bulk for your database operations. DynamoDB also includes storage costs. You pay for the amount of data stored in your tables and any global secondary indexes. The cost is based on the total size of items, measured in gigabytes per month. So keeping your items lean and eliminating unnecessary attributes can go a long way in keeping costs low. And then there's data transfer pricing. Data transferred within the same AWS region is usually free. But if you're using global tables, which replicate data across multiple regions, you'll incur cross-region data transfer costs. This is important to factor in if you're building a global application. To help manage costs, DynamoDB supports time to live, or TTL, which allows you to set expiration times for items. When an item reaches its expiration time, DynamoDB automatically deletes it, freeing up storage and saving you money. It's ideal for session data, temporary cache entries, or logs that only need to be stored for a limited time. And finally, AWS gives you tools like Cost Explorer, CloudWatch, and budgets to monitor your DynamoDB usage and avoid surprises on your bill. You can set alarms for when usage crosses thresholds, or even automate cost optimization based on real-time metrics. In the end, whether you go with on-demand, provisioned, or a mix of both, DynamoDB offers a pricing model that adapts to your needs. Understanding how it works empowers you to build scalable applications that are not only high performance, but also cost-efficient. Global tables and multi-region replication. Imagine your app has users all over the world. Someone in Tokyo updates their profile, and within seconds, A user in Paris needs to see that change. Or maybe you're running a global e-commerce platform where customers in different regions access the same catalog, make purchases, and expect instant updates no matter where they are. This is where DynamoDB Global Tables step in. Global Tables let you create a fully replicated, multi-region, multi-master database. That means your data isn't just copied across regions. It's fully active in every region you choose, and users in those regions can read and write to the database independently, with DynamoDB handling the replication for you automatically. At the core of global tables is eventual consistency. When data is written in one region, DynamoDB replicates it to the other regions asynchronously. While the replication is fast, usually within a second or two, it's not instant, so your app should be designed to tolerate brief delays. For many use cases, this is more than fast enough. The beauty of global tables lies in its simplicity. You don't have to build a custom replication system or maintain separate databases in each region. You define the regions you want, say North Virginia, London, and Singapore, and DynamoDB keeps them in sync behind the scenes. Because global tables are multi-master, writes can happen in any region. That gives you low latency access for users no matter where they are. A user in Germany can write to a DynamoDB table in Frankfurt, while a user in Canada writes to the same table in Montreal, and both can see each other's updates shortly afterward. But with that power comes responsibility. Conflict resolution is an important part of the equation. If two different regions update the same item at nearly the same time, DynamoDB resolves the conflict using a last writer wins strategy, based on a timestamp. This means the version of the item with the most recent update takes precedence, and the other is overwritten. So it's essential that your application logic accounts for that possibility and that your writes are idempotent where needed. Global tables also provide resilience. If one region goes down, your application can automatically fail over to another region and keep running with full read and write access. That kind of availability used to require complex architecture and custom coding. With DynamoDB, it's built right in. Now, let's talk about cost. Each replicated write between regions incurs a charge, and you also pay for storage and read/write capacity in each region. So while global tables give you incredible performance and availability, they do come with additional cost considerations. It's smart to use them for workloads where global performance and fault tolerance really matter, like multiplayer games, real-time collaboration tools, or international commerce platforms. It's also worth noting that you can use global tables with either on-demand or provision capacity modes, giving you flexibility based on your scaling needs. And if your application grows or shifts, you can add or remove regions over time. In a world that's increasingly global and always online, global tables provide a way to meet your users where they are, instantly, reliably, and at scale. Let's explore data modeling with real-world use cases first, then we'll flow smoothly into DynamoDB streams and Lambda triggers in the same audiobook tone. Data modeling in DynamoDB isn't just about storing information. It's about shaping your data so your application can access it quickly, efficiently, and in the fewest number of operations possible. The key difference with DynamoDB is that you model your data based on how you access it, not just how it's related. Let's walk through a few real-world examples to see what this means in practice. Imagine you're building a social media platform. You have users, posts, comments, likes, and followers. In a traditional relational database, you might have a separate table for each entity and use foreign keys to connect them. But in DynamoDB, you want to model everything based on how it will be queried. Suppose a user opens their app and expects to see a feed of recent posts from people they follow. One way to model this is to use a single table where the partition key is the user ID, and the sort key includes a timestamp or post ID. This way, fetching a user's feed becomes a single query that returns all relevant posts in order. You avoid joins and multiple queries. And if you need to pull in comments or likes, you might include those as separate items in the same partition, still accessible through a single efficient query. Now imagine you're building an e-commerce store. You have customers, products, orders, and shipments. Let's say you want to show a user all their past orders, including line items and shipping statuses. You can use a composite key where the partition key is the customer ID, and the sort key starts with a prefix like order hash followed by the order ID. Line items and shipments can be stored as items with sort keys like item hash or shipment hash under the same customer partition. This way, querying all order-related data is fast and scoped to one user. Another great use case is a real-time leaderboard for a game. You might have a table with a partition key of leaderboard and a sort key based on score or time. This lets you easily fetch the top players, sorted in the right order, using a single query. You can also use global secondary indexes to allow filtering by country or game mode, without duplicating your entire dataset. These examples show the importance of prefixes in sort keys. Using values like order hash or post hash helps you identify item types and organize data logically within a single table. It also makes querying for a specific subset of data, like all orders or just the latest posts, simple and efficient. When you approach modeling in DynamoDB, ask yourself, what questions will my app ask this table? If you can answer that, you're already halfway to a great design. Now, let's shift gears and talk about DynamoDB streams and Lambda triggers, two features that add serious muscle to your data workflows. DynamoDB streams capture a time-ordered sequence of item-level changes in your table. Every time an item is added, updated, or deleted, a record appears in the stream. This is incredibly useful when you want to react to changes in real time, without polling or writing extra code to track what changed. By enabling streams on your table, you can integrate with AWS Lambda, allowing you to run functions automatically in response to changes. For example, if a new order is placed in your e-commerce app, a Lambda function can process that order, send a confirmation email, or update inventory, all without manual intervention. Or imagine a chat app where every new message should be broadcast to connected clients in real time. You can write a Lambda function triggered by DynamoDB streams to push those messages to WebSocket connections or notify external APIs. You can even use streams for audit logging. Every change that flows through the stream can be captured and written to another system like Amazon S3 or Elasticsearch for analytics, security, or compliance. Each stream record contains the key attributes of the changed item and, optionally, the entire item before and after the change. This makes it easy to detect exactly what changed and why it matters. And because Lambda is serverless, you don't need to manage any infrastructure. It just works when the data changes. DynamoDB streams can process millions of records with high reliability and scalability. And since they integrate directly with Lambda, you can build event-driven architectures that are elegant, efficient, and cost-effective. Together, data modeling, streams, and triggers give you not just a database, but a full-featured platform for building responsive, scalable, real-world applications. Security best practices in DynamoDB. When it comes to data, security isn't an option, it's a responsibility. And with DynamoDB, AWS gives you a solid foundation of tools to help you build secure applications from day one. Let's start with encryption. By default, DynamoDB encrypts all your data at rest using AWS Key Management Service, or KMS. This means that even if someone were to gain access to the physical storage, they wouldn't be able to read the data without the encryption keys. You can stick with the default AWS managed keys, or, if you need tighter control, use your own customer managed keys. Either way, encryption is always on and handled automatically, no code required. Then there's authentication and access control. Every request to DynamoDB must be signed with valid AWS credentials. This ensures that only authorized users or services can access your tables. To manage permissions, DynamoDB integrates seamlessly with AWS Identity and Access Management, or IAM. You can create fine-grained policies that define exactly what actions a user or application can take. For example, one user might be allowed to read items but not write them. Another might be restricted to just a single table, or even specific items within that table. Fine-grained access control goes even further. You can write IAM policies that allow or deny access based on the content of items, like attributes or partition keys. This is especially useful in multi-tenant applications, where different users should only be able to see their own data. It helps you enforce security at the data level, without adding complex filtering logic in your code. Let's not forget VPC endpoints. These let you connect to DynamoDB from within your private cloud environment, without sending traffic over the public internet. It's a great way to enhance security for back-end systems, especially in regulated industries like finance or healthcare. DynamoDB also supports CloudTrail logging, so every API call is recorded. This includes reads, writes, and management operations. You get a complete audit trail of who accessed what, when, and from where, critical for compliance, troubleshooting, and detecting suspicious activity. Another best practice is to use least privilege. When you create IAM roles or user accounts, only grant the permissions that are absolutely necessary. Start with restrictive policies and open them up only as needed. It's easier to loosen tight security than to fix a breach caused by overly broad access. You should also consider protecting against denial of service attacks. DynamoDB is inherently resilient, but it's still a good idea to use AWS WAF and API Gateway rate limiting if your database is exposed through a public API. These tools can help shield your backend and absorb malicious traffic before it ever reaches your data layer. And finally, automate your security checks. Use AWS config to detect changes in DynamoDB settings, or set up Lambda functions that monitor and respond to suspicious patterns. Security should never be a one-time setup. It's an ongoing process, and automation can help you stay ahead of the curve. At the end of the day, building a secure application on DynamoDB isn't about a single feature. It's about a layered approach: encryption, access control, network isolation, logging, monitoring, and smart design choices, all working together to protect what matters most: your data. Backups and restore. Data loss is every developer's nightmare, but with DynamoDB, backing up and restoring your data is painless and powerful. AWS offers both on-demand and continuous backup options, so you're covered whether you want to back up your table once or preserve every change over time. With on-demand backups, you can create a full snapshot of your table at any point with just a single API call or a few clicks in the console. These backups don't affect performance or availability. You can back up a table no matter how large it is, even in production, and it won't interrupt reads or writes. Restoring from a backup is just as simple. You can choose the backup you want, give your new table a name, and DynamoDB handles the rest. It's a great way to roll back after a critical bug or migrate data between environments. For more advanced scenarios, point-in-time recovery is a lifesaver. When enabled, DynamoDB automatically captures every change made to your table over the past 35 days. This means you can restore your table to any second within that window. Accidentally deleted something yesterday? No problem. Just roll back to the moment right before the mistake. This is especially useful for applications with frequent changes or sensitive data. Both features, on-demand backups and point-in-time recovery, are charged based on storage and activity, so you only pay for what you use. And because backups are encrypted, your data remains secure even in storage. One thing to keep in mind: global secondary indexes are not included in backups, but they can be recreated after restore. Also, backup and restore don't support cross-region functionality natively, so if you need global backups, consider using replication or exporting to S3. Performance optimization tips. DynamoDB is fast by design, but a few smart practices can push it even further. Start with your data model. Remember, DynamoDB performs best when your access patterns align with your partition keys. Skewed keys, or keys that get accessed far more than others, can lead to hot partitions. A hot partition is like a traffic jam. It slows things down. You can avoid this by distributing reads and writes across many partition keys, and by adding randomness to keys when needed. Next, watch your item size. Smaller items are faster and cheaper to read and write. DynamoDB has strict limits, 400 kilobytes per item, so keep payloads tight. If you need to store large blobs or files, consider using S3 and storing a reference in DynamoDB. Make good use of global secondary indexes for alternative query patterns. Just be mindful that indexes consume write capacity, since changes in the base table must be reflected in the indexes too. Only create the indexes you actually need. For read-heavy workloads, enable DAX, the DynamoDB accelerator. This in-memory cache dramatically reduces read latency to microseconds, perfect for real-time apps, leaderboards, or dashboards. To track and tune performance, turn on CloudWatch metrics. Monitor things like read and write throttle events, consumed capacity, and latency. These help you spot inefficiencies early and adjust your capacity or access patterns accordingly. And finally, use batch operations where possible. Instead of sending individual getItem or putItem requests, use batch getItem or batch writeItem to reduce network overhead and improve throughput. Comparing DynamoDB with Google Cloud SQL and Azure Cosmos DB. Let's zoom out and put DynamoDB in context with other major cloud databases, specifically Google Cloud SQL and Azure Cosmos DB. Starting with Google Cloud SQL, it's a managed relational database service that supports MySQL, PostgreSQL, and SQL Server. It's built for structured data with complex relationships. You get joins, transactions, and a traditional SQL experience. But that power comes at a price. Scaling Cloud SQL typically involves vertical scaling, adding more CPU or RAM to a single instance. That works up to a point, but doesn't match the massive, distributed scalability of DynamoDB. DynamoDB, by contrast, is a fully managed NoSQL key value and document database. It scales horizontally with ease, handles millions of requests per second, and is ideal for applications that need speed and flexibility more than strict relationships. It's serverless, auto-scaling, and designed for near-instant reads and writes. You sacrifice relational features, but gain speed, simplicity, and scale. Then there's Azure Cosmos DB, Microsoft's answer to cloud-native NoSQL. Like DynamoDB, Cosmos is globally distributed and supports multi-region writes, automatic sharding, and low-latency reads. It also supports multiple data models, document, key value, graph, and column family, plus APIs compatible with MongoDB, Cassandra, and SQL. Cosmos DB shines in its flexibility and global performance, but it can be more complex to configure and tune. Pricing is also more granular. with throughput measured in request units per second, RU/S, which can be confusing at first. In terms of developer experience, DynamoDB is clean, direct, and tightly integrated into the AWS ecosystem. If you're already on AWS, it's hard to beat. Cloud SQL is great for legacy applications or complex relationships. Cosmos DB is ideal for multi-model, global apps on Azure. Ultimately, the right choice depends on your use case. If you need high-speed, highly scalable, serverless NoSQL with minimal maintenance, DynamoDB delivers. If you're building around relational logic or need SQL, Cloud SQL might be a better fit. And if you're in the Microsoft world and want a multi-model global solution, Cosmos DB offers great versatility. Let's dive into the limitations of DynamoDB, because while it's a powerful and scalable NoSQL database, it's not perfect for every situation. Understanding these constraints helps you design smarter systems and avoid surprises down the line. Data modeling complexity. Unlike relational databases, DynamoDB doesn't support joins, foreign keys, or complex queries. You can't just ask for all users who bought a product and also left a review. Instead, you must design your table and access patterns ahead of time, often combining multiple types of data into a single table. This forces you to think more like a systems engineer than a traditional database designer. Then there's the 400 kilobytes item size limit. Each individual item you store, whether it's a document, a user profile, or a blog post, must be less than 400 kilobytes. That might seem like a lot, but it rules out storing large images, videos, or massive JSON blobs. For big payloads, you'll need to offload to Amazon S3 and keep only the metadata in DynamoDB. DynamoDB also has limited query flexibility. You can't run ad hoc queries with arbitrary filters the way you would in SQL. You can only query based on the primary key or secondary indexes that you've defined up front. That means no where age greater than 30 and country equals Germany unless you've already modeled for it. And about those secondary indexes, they're useful but come with limits. Each table can have up to 20 global secondary indexes and 5 local secondary indexes. Plus, indexes increase your write costs, since updates to the base table must be reflected in the indexes too. Another thing to keep in mind is eventual consistency. By default, DynamoDB returns eventually consistent reads unless you explicitly ask for strongly consistent ones. That means a read might not reflect the very latest write for a short time. This is usually fine, but for use cases like financial transactions or critical logs, you might need to enforce strong consistency, or use a different database altogether. Also, there's no built-in support for complex transactions across multiple tables. DynamoDB does support ACID transactions, but only within a limited scope, 25 items max or 4 megabytes of data per transaction. It's great for atomic updates but not a full replacement for relational transactional systems. Hot partitions can also be a pain. If you use the same partition key too often, say, writing all user activity logs under a single user ID, you create uneven traffic that leads to throttling. Avoiding this requires clever key design and sometimes even artificial sharding. On the operational side, DynamoDB's pricing model can be tricky. You pay for reads, writes, storage, and data transfer, and charges can spike if your app suddenly scales or your access patterns change. Capacity planning, especially for provisioned mode, can take some work. And finally, vendor lock-in is real. DynamoDB is an AWS native service, and while it offers amazing integration with AWS tools, it's not portable. Migrating to or from DynamoDB is not as easy as exporting a SQL dump. Once you go deep into DynamoDB's ecosystem, switching to another database takes planning, time, and effort. To sum it up, DynamoDB is a beast when it comes to scale, speed, and simplicity, but only if your workload fits the NoSQL model. If you need joins, large item storage, or complex querying, it might not be the right fit. But if your application is designed with DynamoDB's strengths in mind, it can be a lightning-fast, rock-solid foundation for modern cloud-native apps. Perfect. Let's explore caching patterns and multi-tenant design in DynamoDB, two advanced topics that can seriously level up the performance and flexibility of your application. Caching patterns with DynamoDB. DynamoDB is fast, but sometimes you need blazing fast. That's where caching comes in. Caching helps reduce latency, offload pressure from your database, and save costs by reducing read requests. The key is knowing what to cache, when, and where. The most common pattern is read-through caching, often using DynamoDB Accelerator, or DAX. DAX is an in-memory cache that sits between your application and DynamoDB. When your app tries to read an item, DAX checks if it already has it cached. If not, it fetches it from DynamoDB, returns it to the app, and stores it in memory for next time. The beauty of DAX is that it's API compatible with DynamoDB, so you don't need to change your codebase much. And it can reduce read latency from single-digit milliseconds to microseconds. Another pattern is write-through caching, where you write to both the cache and the database at the same time. This ensures the cache always has the freshest data, which is useful for frequently accessed items like user profiles or product metadata. Then there's lazy caching, where you only cache data after it's first requested. If the cache misses, you fetch it from dynamodb and store it in memory for a short period, like 5 minutes or 1 hour. This works well for rarely updated, read-heavy data. You can use services like Amazon Elasticache with Redis or Momcached for this approach. For data that changes often but doesn't need to be consistent in real time, use time to live, TTL. TTL automatically expires cached items after a set period. It's great for search results, dashboard views, or notifications, where eventual freshness is okay. One more trick is session caching. If your application needs to store user-specific session data, like shopping cart contents or preferences, you can use a short-lived in-memory cache keyed by session ID. This reduces round trips to DynamoDB for every page load. No matter which pattern you choose, caching is about trade-offs. You're balancing speed and cost against data freshness. The best pattern depends on how often your data changes and how important it is to reflect those changes immediately. Multi-tenant design in DynamoDB. DynamoDB is great for SaaS applications where multiple customers, or tenants, share the same infrastructure. But you'll need a solid strategy for multi-tenant design to keep things secure, scalable, and manageable. There are 3 main approaches: single table design, separate tables per tenant, and hybrid models. In a single table multi-tenant model, all tenant data goes into the same table. You include a tenant_ID in every item and use it as part of your partition key. For example, you might design your key like tenant_ID-user_ID. This ensures tenant data stays logically separated. You can also use IAM fine-grained access control to make sure tenants can only access their own data. This model is cost-effective, easy to scale, and great for smaller tenants. But what if one tenant grows rapidly? That's where table per tenant comes in. Each tenant gets its own dedicated DynamoDB table. This gives you full isolation and makes it easy to scale or tune performance per tenant. It also makes auditing and backup simpler. The downside is that managing hundreds, or thousands, of tables can be a headache. You'll need automation for provisioning, monitoring, and billing. The third option is a hybrid model. Use a shared table for small tenants and dedicated tables for large, high-traffic ones. This gives you the cost savings of a single table and the isolation benefits of dedicated tables, depending on tenant size and usage patterns. Regardless of the approach, you should implement tenant-aware access control. Use IAM policies or application logic to enforce that one tenant can't access another's data. Fine-grained access control in DynamoDB makes this easier by allowing you to define rules at the item level. It's also important to track usage per tenant, either by tagging items or integrating with CloudWatch and AWS billing tools. This lets you monitor performance, detect abuse, and even enable tenant-level billing or throttling. Another tip? Design your partition keys to evenly distribute load. If one tenant generates most of the traffic, you risk creating a hot partition. To avoid this, include some randomness or timestamp-based sharding in the key structure. In summary, caching patterns and multi-tenant design are essential tools for scaling your DynamoDB-powered application. Whether you're cutting down latency with DAX or designing for thousands of tenants in a single table, these techniques unlock the full potential of DynamoDB. Absolutely, this is a crucial topic, especially as modern applications move toward distributed, cloud-native architectures. Let's dive into microservice patterns with respect to databases, particularly how they relate to scaling transactions to support millions of users. When you build applications as microservices, each service is designed to be small, independent, and focused on a single responsibility. A key part of this independence is data ownership, meaning each microservice manages its own data, ideally in its own isolated database. This prevents tight coupling between services and avoids bottlenecks when scaling. Now, DynamoDB fits this pattern beautifully. It's fully managed, scales automatically, and supports independent access patterns. So in a microservices architecture, you can give each service its own DynamoDB table, completely isolated and optimized for that service's needs. But how do you handle transactions across multiple services, especially when millions of users are making purchases, submitting forms, or transferring money simultaneously? Let's explore that. Single responsibility, single table. Each microservice owns its own table, and all business logic related to that data is handled by the owning service. For example, the order service might own a table called orders, while the payment service has a separate payments table. This model eliminates shared databases and ensures services can scale independently. It's clean, efficient, and great for horizontal scaling. However, it introduces complexity when multiple services need to coordinate around a shared operation. Distributed transactions and the saga pattern. Let's say a user places an order, which needs to reserve stock, charge their card, and send a confirmation email. In a monolithic app, this might be a single SQL transaction. But in microservices, each of these actions touches different services and different tables. Enter the saga pattern. A saga breaks a transaction into smaller, coordinated local transactions. Each step in the saga performs a local operation and publishes an event. The next service listens for that event, performs its part, and emits a new event. If something fails, compensation logic is triggered to roll back prior steps. For example, the order service creates an order and publishes an order-created event. The inventory service reserves stock and emits a stock-reserved event. The payment service charges the customer and emits a payment-succeeded event. If payment fails, a payment-failed event can trigger a rollback, like releasing stock or canceling the order. With DynamoDB and microservices, you use event-driven architecture and DynamoDB streams to implement sagas. Each step in the process is lightweight, fast, and isolated. This makes it possible to process millions of transactions in parallel, without global locks or database contention. Idempotency and message deduplication. When scaling to millions of transactions, idempotency becomes crucial. It ensures that if a service receives the same event twice, due to retries or network issues, it doesn't process it twice. Each operation must be designed to be safely repeated. For example, before writing a payment transaction to DynamoDB, the payment service might check if the transaction _id already exists. If it does, it skips the write. This simple check ensures consistency in a massively parallel system. AWS tools like SNS, SQS, and Lambda also help build scalable, resilient microservices with built-in retries and deduplication logic. Combined with DynamoDB streams, this gives you a powerful event pipeline. Scaling DynamoDB for millions of users. DynamoDB scales horizontally by design. You don't have to provision servers or manage clusters. But to truly handle millions of concurrent users, you must design your tables to avoid bottlenecks. Use partition keys that spread load evenly. Avoid hotkeys that receive too many reads or writes. For example, instead of user_id alone as a key, combine it with a timestamp or random suffix. Use autoscaling or on-demand capacity to absorb traffic spikes. Use DAX to cache hot data and reduce read load. And use global tables for low latency writes and reads across multiple AWS regions, critical when your users are distributed worldwide. In short, scaling to millions of transactions in a microservices world isn't about making a bigger database, it's about designing for independence, event coordination, safe retries, and intelligent partitioning. DynamoDB's strengths, serverless, scalable, event-aware, make it a natural fit for this world. A common algorithm for ensuring correct completion of a distributed transaction is the two-phase commit, 2PC. This algorithm is usually applied for updates able to commit in a short period of time, ranging from couple of milliseconds to couple of minutes. There are also long-lived distributed transactions, for example a transaction to book a trip, which consists of booking a flight, a rental car and a hotel. Since booking the flight might take up to a day to get a confirmation, two-phase commit is not applicable here. It will lock the resources for this long. In this case, more sophisticated techniques that involve multiple undo levels are used. The way you can undo the hotel booking by calling a desk and canceling the reservation. A system can be designed to undo certain operations, unless they are irreversibly finished. A two-phase commit, 2PC, is a protocol used in databases to ensure that transactions, especially ones involving multiple systems, are completed successfully and consistently. It's kind of like making sure everyone involved in a group decision is on the same page before finalizing things. Let me break it down in simple terms. Imagine you're organizing a big group dinner at a restaurant. First phase, the decision phase. You, the organizer, ask everyone in the group if they are okay with the plan for dinner. They each reply with a yes or no. If everyone says yes, the dinner plan is good to go, and you can move to the next step. If even one person says no, you can't go ahead with the plan. Second phase, the commitment phase. Once you've got everyone's yes, you tell the restaurant to prepare the dinner and confirm the booking. Everyone is now committed to the plan. If all the group members said yes, the dinner happens as planned. If one person says no during the first phase, the whole dinner plan is cancelled. You stop everything, and no one is expected to pay or show up. Now, apply this to databases. In a distributed system, you might need to update multiple databases or services. The first phase is like asking each service/database if it's ready to commit the transaction. The second phase is when all systems say yes, and the transaction is officially committed. If any system says no, like the first person in our dinner group saying they can't come, the transaction is rolled back, and no changes are made. In short, a two-phase commit ensures that either all parts of the transaction succeed or none of them do. It's a way to make sure things are consistent and no one ends up with a half-finished operation.